bases and salts. Acids, bases and salts. We know that lemon juice, tomatoes and unripened grapes have a sour taste because they contain acidic substances. We are also familiar with reagents like hydrochloric acid, nitric acid and sulfuric acid. They are important acids used in the laboratory. Substances like caustic soda, caustic potash, magnesium hydroxide, ammonium hydroxide and lime, tuna or calcium oxide are bitter in taste and soapy to touch. They are called bases or alkalis. Acids and bases react to form compounds known as salts. Acids and bases. The Latin word acidus means sour. Substances that are sour to taste and have acidic ingredients are called acids. Chemical substances that are bitter to taste are called bases. Understanding the chemical properties of acids and bases. Testing of acids and bases. How can we test acidic and basic substances? We can test these substances by using an indicator like litmus paper. Indicators. Substances which change color in acids or bases are called indicators. Litmus papers are prepared using a solution of litmus. They are used as indicators. Acids turn blue litmus red and bases turn red litmus blue. Litmus is a natural indicator. Litmus is obtained from a plant named lichen which belong to the division Thallophyta. We can prepare many other natural indicators using various natural substances like purple or red cabbage, beetroot, some brightly colored flowers like purple and red bougainvillea, and hibiscus flowers. Let us perform an activity using some natural indicators. Activity: we shall prepare extracts from natural substances like beetroot, China rose petals, turmeric, and indigo. These extracts can be used as natural indicators. First, we shall prepare an extract of beetroot. Crush some beetroot in a mortar. Add sufficient water to obtain the extract. Now, filter it using a filter paper and collect the filtrate in a beaker. This is the beetroot extract. Similarly, prepare extracts of China rose petals, turmeric, and indigo. Keep the extracts in 4 watch glasses. Dip small strips of filter paper in these extracts for some time. Now, remove them and dry them thoroughly. Using these natural indicator strips, we shall now test solutions of lemon juice, common salt, baking soda, vinegar, and edible oil. Dip a strip of each natural indicator in the different test solutions. Note the color change and tabulate the results. We shall begin with strips of beetroot extract. A beetroot strip turns red in lemon juice and vinegar. In baking soda, it turns blue. In common salt solution and edible oil, it remains same. Turmeric paper strip remains yellow in lemon juice and vinegar. In baking soda, it turns red. In common salt solution and edible oil, it remains yellow. Indigo strip remains blue in all the solutions. A China rose petal strip turns pink in lemon juice and vinegar. In baking soda, it turns green. In common salt solution and edible oil, it remains red. There are certain chemical substances like phenolphthalein, methyl orange and eosin that are called synthetic indicators. Let us perform an activity using synthetic indicators. Activity: we shall test solutions of vinegar, lime juice, ammonium hydroxide and hydrochloric acid using indicators like phenolphthalein, methyl orange and litmus paper. Note the color change and tabulate the observations. Let us first test each of the solutions with red litmus paper. What do you observe? In vinegar, lime juice and hydrochloric acid, red litmus paper does not show any change in color, but in ammonium hydroxide solution, it turns blue. Now, test each solution with blue litmus paper. Which of the solutions show a color change? Well, vinegar, lime juice and hydrochloric acid change the color of blue litmus paper to red. However, in ammonium hydroxide solution, there is no change in color. Take about 5 ml of each solution in different test tubes. Let us add a few drops of phenolphthalein indicator to each of the solutions. Note the color change. Phenolphthalein indicator does not show any change in color in vinegar, lime juice and hydrochloric acid, but in ammonium hydroxide it turns pink. Take about 5 ml of each solution in different test tubes. Add a few drops of methyl orange indicator to each solution and note the color change. In vinegar, lime juice and hydrochloric acid, methyl orange turns pink. In ammonium hydroxide, it turns yellow. On the basis of these observations, can we identify the nature of the solutions? Yes, we can. We know that red litmus turns blue in basic solutions and blue litmus turns red in acidic solutions. We may conclude that vinegar, lime juice and hydrochloric acid are acidic in nature. Ammonium hydroxide is basic in nature. Hence, we can say that phenolphthalein remains colorless in acidic solution and changes from colorless to pink in basic solutions. Methyl orange changes from orange to pink in acidic solutions and from orange to yellow in basic solutions. There are some indicators called olfactory indicators. They exhibit a change in their odor in acidic or basic solutions. Examples of olfactory indicators are onion, vanilla extract, and clove oil. All these substances have a characteristic smell. When an acid or a base is added to these substances, their characteristic smell cannot be detected. Let us perform an experiment using onion extract and vanilla essence. When dilute hydrochloric acid is added to test tubes containing onion extract and vanilla essence, the original smell of onion and vanilla does not change. This shows that an acidic solution like hydrochloric acid does not destroy the smell of onions and vanilla. But when sodium hydroxide is added to test tubes containing both these substances, the characteristic smell of the onion and vanilla is not detectable. This can be used as a test for acids and bases. Reactions of acids and bases with metals. Activity: we shall test the metals magnesium, zinc, copper and iron using different acids. Let us also observe what happens when we hold a burning candle near the gas evolved. Take a test tube, add a piece of magnesium. Then add a few drops of dilute hydrochloric acid to it. Fix a bent tube and carefully hold a burning candle at the other end of the bent tube. The gas evolved burns with a popping sound and the candle extinguishes. Let us see the reaction. Magnesium reacts with dilute hydrochloric acid to form magnesium chloride and hydrogen gas. Now, let us test zinc granules and copper granules using dilute sulfuric acid, dilute nitric acid, and acetic acid. Reaction of zinc granules with dilute sulfuric acid. When zinc reacts with dilute sulfuric acid, a gas is evolved. This gas burns with a popping sound and the candle extinguishes. Zinc reacts with dilute sulfuric acid to form zinc sulfate and hydrogen gas. Reaction of zinc granules with dilute nitric acid. When zinc reacts with dilute nitric acid, a gas is evolved. This gas evolved does not produce any effect on the burning candle. Zinc reacts with dilute nitric acid to form zinc nitrate, water, and nitrous oxide. Reaction of zinc granules with dilute acetic acid. When zinc reacts with dilute acetic acid, a gas is evolved. This gas burns with a popping sound and the candle extinguishes. Zinc reacts with acetic acid to form zinc acetate with the liberation of hydrogen gas. Reaction of copper granules with dilute sulfuric acid. Copper does not react with dilute sulfuric acid. Reaction of copper granules with dilute nitric acid. When copper reacts with dilute nitric acid, a gas is evolved. This gas evolved does not produce any effect on the burning candle. Copper reacts with dilute nitric acid to form copper nitrate, water, and nitric oxide. Reaction of copper granules with dilute acetic acid. Copper does not react with acetic acid. What is the reaction between iron nails and concentrated hydrochloric acid? When iron nails react with concentrated hydrochloric acid, a gas is evolved. This gas burns with a popping sound and the candle extinguishes. Iron reacts with concentrated hydrochloric acid to form iron chloride and hydrogen gas. How does zinc react with dilute hydrochloric acid? Zinc reacts with dilute hydrochloric acid to form zinc chloride and hydrogen gas. From these experiments, we can say that reactive metals like magnesium, zinc, and iron react with hydrochloric acid to produce the corresponding salt and hydrogen gas. Less reactive metals like copper do not react with hydrochloric acid. The general reaction is that an acid reacts with a metal to form salt and hydrogen gas. That is the reason why we do not keep curd or other sour substances in metal vessels like brass or copper. The acids present in these foodstuffs can react with the metal of the vessel and form poisonous metal compounds which can cause food poisoning and damage our health. How do metals react with bases? Let us perform an activity to understand this. Activity: take a few pieces of aluminium ribbon in a test tube and add some sodium hydroxide. Warm the test tube. What do you observe? Aluminium metal dissolves in sodium hydroxide and there is evolution of a gas. Aluminium reacts with sodium hydroxide to form an aluminate of sodium and hydrogen gas. How does zinc react with sodium hydroxide? Zinc reacts with sodium hydroxide to form sodium zincate and hydrogen gas. Do all metals react with bases in the same way? Only reactive metals like sodium, potassium and lithium react with bases. Less reactive metals like copper, silver and gold do not react with bases. Let us now perform an activity to understand the reactivity of acids towards carbonates and bicarbonates of metals. Reactions of acids with metal carbonates and bicarbonates. Activity. Take some aluminium carbonate in a test tube. Add some dilute hydrochloric acid. Let the evolved gas pass through the delivery tube and allow it to react with lime water. What do you observe? The lime water has turned milky. Let us see the reaction taking place. Aluminium carbonate reacts with dilute hydrochloric acid to form aluminium chloride, water and carbon dioxide. The carbon dioxide evolved reacts with lime water to give a precipitate of calcium carbonate. This makes the lime water milky. If the carbon dioxide gas is allowed to react for a longer time, calcium carbonate reacts with carbon dioxide to form soluble calcium bicarbonate. Thus, the solution becomes colorless. What would happen if a burning candle is brought near the gas evolved? The burning candle would extinguish. Carbon dioxide does not burn, nor does it support combustion. Please note that chalk, limestone and marble are the different forms of calcium carbonate. Another metal carbonate which we are familiar with is washing soda or sodium carbonate. How will it react with hydrochloric acid? Sodium carbonate reacts with hydrochloric acid to give sodium chloride, water and carbon dioxide. What will be the reaction of baking soda with hydrochloric acid? Baking soda or sodium bicarbonate reacts with hydrochloric acid to give sodium chloride, water and carbon dioxide. From these reactions, we can say that metal carbonates and bicarbonates react with hydrochloric acid to form the corresponding salt, water and carbon dioxide. Now let us perform an activity to see the reactions of acids with metallic oxides. Reactions of metallic oxides with acids. Activity. Take a small amount of copper oxide in a test tube. Add to it a few drops of dilute hydrochloric acid. What do you observe? The solution turns green. What is the reaction? Copper oxide reacts with dilute hydrochloric acid to form copper chloride and water. All metal oxides react with acid to form the corresponding salt and water. Do metal oxides react with alkalis? No, metal oxides are basic in nature. Hence, they do not react with alkalis. They react only with acids to neutralize them. Let us now study the reactivity of bases with non-metallic oxides. Reactions of non-metallic oxides with bases. We have seen the reaction between carbon dioxide and lime water. Carbon dioxide reacts with lime water to give a precipitate of calcium carbonate. Carbon dioxide is a non-metallic oxide and lime water, which is calcium hydroxide, is a base. From this reaction, what can we say about the chemical nature of carbon dioxide? Since calcium hydroxide is a base, carbon dioxide should be acidic. Thus, we can conclude that non-metallic oxides are acidic in nature. We know that acids react with bases to form salt and water. Let us now perform an activity to understand this reaction. Reactions of acids and bases with each other. Activity: take about 2 or 3 ml of hydrochloric acid in a test tube. Add a few drops of phenolphthalein indicator. What is the color of the solution? It is colorless. Phenolphthalein is colorless in acids. Now add sodium hydroxide solution drop by drop to this solution. Keep shaking the test tube. There is a slight pink color to the solution, which disappears on shaking the test tube. Now let us add a few more drops. Now there is a color change. The solution has turned pink. This happens because hydrochloric acid has completely reacted with sodium hydroxide to form salt and water. The last drop of sodium hydroxide makes the amount of base excess, and thus the color changes from colorless to pink. Let us see what happens when we add hydrochloric acid to this solution. The color of the solution changes from pink to colorless. This happens because the solution now has excess of hydrochloric acid. This reaction between an acid and a base to produce salt and water is called a neutralization reaction. This also means that the reaction between a base and a non-metallic oxide, which is acidic in nature, is called a neutralization reaction. We use the words bases and alkalis. In what way are they different? All bases do not dissolve in water. The bases which dissolve in water are called alkalis. Alkalis are soapy to touch, bitter to taste, and corrosive. All alkalis are bases, but all bases are not alkalis. Examples of bases are calcium oxide, magnesium oxide, and copper oxide. Example of alkalis are sodium hydroxide and potassium hydroxide. We know that acids are sour to taste, but do not attempt to touch them or taste them. They are very harmful. Ionization of acids and bases. We know that an acid is a compound which, when dissolved in water, gives hydrogen ions. Hydrochloric acid, when dissolved in water, produces hydrogen ions and chloride ions. A base is a substance which dissolves in water to produce hydroxide ions in solution. Sodium hydroxide, when dissolved in water, produces sodium ions and hydroxide ions. Let us perform an activity to understand ionization of acids and bases. Activity: Take about 25 ml of sugar solution in a beaker. Dip 2 carbon rods in it. They are the electrodes. Electrodes are the points at which the electric current enters or leaves the solution. Connect the electrodes to two terminals of a 6-volt battery through a bulb and a switch. Now switch on the current. What do you observe? Does the bulb glow? No, the bulb does not glow. Repeat the experiment by replacing the sugar solution in the beaker by dilute hydrochloric acid. Switch on the current. Now the bulb glows. If we replace the solution by dilute sulfuric acid, again the bulb glows. Now take methyl alcohol solution in the beaker. Does the bulb glow? No, it does not. Glowing of bulb indicates that hydrochloric acid and sulfuric acid solution conduct electricity. An aqueous solution of an acid can conduct electricity due to the presence of ions. Hydrochloric acid, when dissolved in water, produces hydrogen ions and chloride ions, which conduct electricity. Hydrogen-containing compounds like sugar and methyl alcohol do not produce hydrogen ions or any other ions in the solution. Thus, due to the absence of ions, these solutions do not conduct electricity. Compounds such as glucose, sugar, and alcohol also contain hydrogen in their molecule, just like in acids, but they are not classified as acids. The reason is that hydrogen present in their molecules does not separate as hydrogen ions on dissolving in water. So we conclude that all acids contain hydrogen, but all hydrogen-containing compounds are not acids. Let us repeat this activity using a basic substance, calcium hydroxide. What do we see? The bulb glows. An aqueous solution of a base can conduct electricity due to the presence of ions. Calcium hydroxide, when dissolved in water, produces calcium ions and hydroxide ions, which conduct electricity. We can conclude that all acids and bases conduct electricity. Acids and bases conduct electricity due to formation of ions in aqueous medium. Behavior of acids and bases in an aqueous medium. Activity: take about 0.5 grams of copper chloride in a test tube. Add a few drops of concentrated sulfuric acid. There is a gas evolved. Now, test the gas with dry and wet litmus papers. First, we shall try with a dry blue litmus paper. Is there any change? No, there is no change in the color of the litmus paper. Now, hold a moist blue litmus paper. What do you observe? The moist blue litmus paper turns red. Dry hydrogen chloride gas does not contain any hydrogen ions. Therefore, it does not show acidic properties. Thus, there was no effect on the litmus paper. However, when hydrogen chloride dissolves in water, it produces hydrogen ions and chloride ions. Therefore, it shows acidic properties. That is the reason why a moist blue litmus paper showed a color change. While doing this experiment, what precautions should be taken in humid conditions? If the climate is humid, we will have to allow the gas produced to pass through a drying tube containing calcium chloride to dry the gas. All acids dissolve in water to produce hydrogen ions. For example, sulfuric acid dissolves in water to produce hydrogen ions and sulfate ions. These hydrogen ions cannot exist alone. They always combine with water to form hydronium ions. Always remember that it is dangerous to add water to an acid. This being an exothermic reaction, a lot of heat is generated. This heat generated may cause splashing of the mixture, which may cause burns. Therefore, one should always add acid to water very cautiously and slowly. How do bases behave when they are dissolved in water? Sodium hydroxide dissolves in water to produce sodium ions and hydroxide ions. All alkalis dissolve in water to produce hydroxide ions. Potassium hydroxide dissolves in water to produce potassium ions and hydroxide ions. Magnesium hydroxide dissolves in water to produce magnesium ions and hydroxide ions. Acids are classified into concentrated acids and dilute acids on the basis of their concentration. Bases are also classified into concentrated bases and dilute bases on the basis of their concentration. A dilute acid is obtained by mixing a concentrated acid with water. Similarly, a dilute base is obtained by mixing a concentrated base with water. Mixing an acid with water results in decrease in the concentration of hydrogen or hydronium ions per unit volume. Similarly, mixing a base with water results in a decrease in the concentration of hydroxide ions per unit volume. Such a process is called dilution, and the acid or base is said to be diluted. Strength of acids and bases. Concentration of hydrogen ions and hydroxide ions and the pH scale. Acids which are completely ionized in water and produce a large number of hydrogen ions in solution are called strong acids. For example, acids like hydrochloric acid, nitric acid and sulfuric acid are strong acids. If hydrochloric acid is dissolved in water, all the hydrogen chloride molecules dissociate to produce hydrogen ions and chloride ions. An acid which is partially ionized in water and thus produces less number of hydrogen ions in solution are called weak acids. For example, acids like acetic acid, citric acid found in oranges and lemons, carbonic acid found in soft drinks, and ascorbic acid are weak acids. If acetic acid is dissolved in water, it produces acetate ions and hydrogen ions. Bases which completely ionize and produce a large number of hydroxide ions in solution are called strong bases. For example, sodium hydroxide and potassium hydroxide are strong bases. If sodium hydroxide is dissolved in water, all the sodium hydroxide molecules dissociate to form sodium ions and hydroxide ions. Bases which partially ionize in water and produce less number of hydroxide ions in solution are called weak bases. For example, ammonium hydroxide dissolves in water to produce ammonium ions and hydroxide ions. The acidity or basicity of a solution is indicated by the pH scale. In the word pH, P stands for potens, which means strength in German language, and H stands for the hydrogen ion concentration. The pH scale ranges from 0 to 14. When the pH value is between 0 and 7, the solution is acidic. When the pH is between 7 and 14, the solution is basic. A neutral solution will have a pH of 7. As the pH of a solution decreases from 7 to 0, the hydrogen ion or hydronium ion concentration goes on increasing. As the pH of the solution increases from 7 to 14, the hydroxide ion concentration in the solution goes on increasing. If the hydrogen ion concentration is equal to the hydroxide ion's concentration, then the pH is 7.0. The pH of a solution is measured using a universal indicator. A universal indicator is a mixture of several indicators. It shows a different color for a different pH. The pH of the solution can be determined by matching the color change obtained with the pH color chart. Let us perform an activity using a universal indicator. Activity: take samples of kokum extract, palak extract, an aerated drink, tomato juice, dilute nitric acid, dilute potassium hydroxide, prepared tea, a mixture of ginger with honey, and buttermilk in different test tubes. Note the color of the solutions before addition of the indicator and enter your observations in your observation table. Add 2 drops of the universal indicator to each of the test tubes and observe the color change. Compare the color change obtained with the pH color chart of the universal indicator and determine the pH of the solution. Enter your observations and results in your observation table. Let us begin with kokum extract. What was the original color? It was magenta red. After addition of the indicator, it has changed to orange. The pH is nearly 4.5. Palak extract was originally green, now it has turned blue-green in color. The pH is nearly 9.5. Aerated drink had a lemony color before addition of the indicator. Now it has turned orange-red. The pH is nearly 2.5. Tomato juice was originally orange-red in color. Now it has turned orange. The pH is nearly 4.0. Dilute nitric acid was originally colorless. Now it has turned red. The pH is nearly 1.0. Dilute potassium hydroxide was originally colorless. Now it has turned violet. The pH is nearly 13.0. Prepared tea was originally brownish orange in color. Now it has turned yellow. The pH is nearly 6.0. A mixture of ginger and honey was originally pale buff in color. Now it has turned yellow. The pH is nearly 6.0. Buttermilk was originally white in color. Now it has turned orange. The pH is nearly 4.5. Importance of pH in everyday life. What is the importance of pH in our everyday life? Our human body works well at a pH of 7.0 to 7.8. Our stomach produces hydrochloric acid, which helps in the digestion of our food. Sometimes, excess of acid is produced in the stomach for various reasons, such as remaining hungry for too long. This excess acid causes indigestion, which produces pain and uneasiness. This condition is called acidity. There are certain chemical substances like milk of magnesia or magnesium hydroxide that can fight acidity. They are called antacids. Antacids neutralize the excess acid caused in the stomach. Like us, plant growth is also affected by varying pH or varying acidity or alkalinity of the soil. Let us perform an activity to understand this. Activity: collect a sample of rainwater and add a few drops of universal indicator. What is the color change? The color changes to yellow. What is the pH? The pH is about 6. That is, rainwater is acidic. This water seeps into the soil and makes the soil also acidic. Highly acidic soils can destroy the roots of the plant and also the nutrients present in the soil. Highly acidic soils also promote the growth of harmful bacteria that adversely affect the growth of plants. Fish and other aquatic life are drastically affected by acidic water. Certain fishes which cannot tolerate highly acidic water eventually die. What is the importance of the pH of our saliva? Our saliva has a certain pH which helps in neutralizing the acid produced after a meal. After a meal, the bacteria in the mouth break down food particles to produce acids. This causes the pH of the saliva to go below 5.5. Although our tooth enamel is made of a hard substance called calcium phosphate, a highly acidic pH can cause tooth decay. Using a toothpaste, which is usually basic in nature for cleaning the teeth, can neutralize the excess acid and prevent tooth decay. We have discussed that highly acidic soils affect plant growth. If the soil is highly acidic, it can be treated with basic substances like quicklime, that is, calcium oxide, or slaked lime, that is, calcium hydroxide, or chalk, that is, calcium carbonate. These substances neutralize the excess acid in the soil and reduce the acidity of the soil. Let us perform an activity regarding testing of soil samples. Activity: take 3 soil samples. Mix some water in each of them. Filter each sample and collect the filtrate in different test tubes. Add a drop of the universal indicator to each of the samples and observe the color. The solution in the first test tube showed a color change to yellow. The pH is nearly 6.0. Which plants grow at pH 6.0? Carrots, sweet potatoes and potatoes grow at this pH. The solution in the second test tube showed a color change to green. The pH is nearly 7.0. Mint or pudina and lettuce grow at this pH. The solution in the third test tube showed a color change to dark green. The pH is nearly 8.0. Cabbage and onion grow at this pH. Carboxylic acids. Certain foods are acidic because of the presence of carboxylic acids. For example, lemon and oranges contain citric acid and ascorbic acid. Tamarind is sour to taste because it contains tartaric acid. Raw milk turns sour due to the formation of lactic acid. Butter contains butyric acid. Roots of the plant valerian contain valeric acid, commonly known as pentanoic acid. Have you wondered why a sting by a red ant causes itching and irritation? This is due to the presence of formic acid in the sting. That is why red ants are known as forma in Greek language. A honeybee sting and stinging hair of the nettle leaves also contain formic acid, which cause a burning sensation. If the affected area is rubbed with a mild base like baking soda, it neutralizes the effect of the acidic liquid and gives relief. Often, we find a plant called the dock plant growing beside the nettle plant. This plant acts as a traditional remedy for the nettle leaf sting. The leaves of the dock plant contain a basic substance which can neutralize the acidic sting of the nettle leaves and give relief. This behavior shown by animals and plants can be termed as a self-defense shown by them. Family of salts. Salts having the same positive ions or the same negative ions are said to belong to a particular family of salts. For example, the salts sodium sulfate, sodium chloride, sodium carbonate, and sodium nitrate belong to the family of sodium salts. They contain the same positively charged ion, sodium ion. Similarly, sodium chloride, potassium chloride, and ammonium chloride contain the same negatively charged chloride ion. Therefore, they belong to the family of the salts called chloride salts. The salts sodium sulfate, calcium sulfate, magnesium sulfate, and copper sulfate contain the same negatively charged sulfate ion. Therefore, they belong to the family of salts called sulfate salts. Salts are formed when an acid is neutralized by a base. Sodium sulfate is a salt of sodium hydroxide and sulfuric acid. Potassium sulfate is a salt of potassium hydroxide and sulfuric acid. Copper sulfate is a salt of copper hydroxide and sulfuric acid. Calcium sulfate is a salt of calcium hydroxide and sulfuric acid. Ammonium chloride is a salt of ammonium hydroxide and hydrochloric acid. Sodium nitrate is a salt of sodium hydroxide and nitric acid. pH of salts. Activity: prepare saturated solutions of common salt, soap, washing soda, and baking soda. Note the colors of all the solutions and enter them in the observation table. All these solutions are colorless. pH of salts. Activity: prepare saturated solutions of common salt, soap, washing soda, and baking soda. Note the colors of all the solutions and enter them in the observation table. All these solutions are colorless. Now add a drop of the universal indicator to each of the solutions and observe the color change and determine the pH. Common salt solution turns green in color. The pH is 7.0. Soap solution turns blue-green in color. The pH is 9.0. Washing soda solution turns dark blue in color. The pH of the solution is 11.0. Baking soda solution turns dark green in color. The pH of the solution is 8.0. On the basis of the pH, let us determine the chemical nature of the solutions. Common salt is neutral in nature. Washing soda, baking soda, and soap are basic in nature. From these pH values, can we identify the strength of the acids and bases from which these are obtained? Yes, we can. The pH of sodium chloride is 7. Therefore, it is a neutral salt. That is, it is a salt of a strong acid and a strong base. If the pH value is less than 7, then the salt is acidic in nature. It will be a salt of a strong acid and a weak base. If the pH value is more than 7, then the salt is alkaline in nature and it will be the salt of a weak acid and a strong base. Common salt is a salt of strong acid and strong base. Washing soda and baking soda are salts of strong bases and weak acids. We know that sodium chloride or common salt is obtained by the reaction between sodium hydroxide and hydrochloric acid. Common salt forms an important constituent of our food. Our food would be tasteless without the use of salt. Let us know more about common salt. Common salt. Seawater contains many salts such as sodium chloride and potassium chloride dissolved in it. Sodium chloride is separated from other salts by evaporating seawater. Underground deposits of common salt are found in several parts of the world. These deposits are often brown-colored due to the presence of impurities in them. These deposits are called rock salt. Impure common salt is brown in color. It becomes colorless and crystalline in nature after it is purified. It is an important raw material in the manufacture of various chemicals like sodium carbonate, sodium bicarbonate, etc. What will happen if electricity is passed through a solution of sodium chloride? If electricity is passed through sodium chloride solution, also called as brine, it decomposes to form sodium hydroxide, chlorine gas and hydrogen gas. This shows that sodium chloride solution can conduct electricity. This process is called electrolysis of sodium chloride solution. Sodium hydroxide, chlorine gas and hydrogen gas are important chemicals that we can obtain from sodium chloride. Chlorine gas is liberated at the anode and hydrogen gas is liberated at the cathode. Sodium hydroxide solution is formed near the cathode. Sodium bicarbonate. Sodium bicarbonate is also known as sodium hydrogen carbonate. Its chemical formula is NaHCO3. It is commonly known as baking soda. This is the soda which is commonly used in making tasty crispy pakoras. It is also used while baking spongy cakes. Baking soda is produced on a large scale by treating a cold and concentrated solution of sodium chloride with ammonia and carbon dioxide. We had earlier checked the pH of baking soda. The pH was 8.0. If we test a solution of sodium bicarbonate with blue and red litmus papers, we observe that the blue litmus paper does not show any change, while red litmus paper turns blue. This shows that sodium bicarbonate is alkaline in nature. Being alkaline, it can be used to neutralize an acid. It is therefore used as an ingredient of antacids. Sodium bicarbonate reacts with excess hydrochloric acid of the stomach to form sodium chloride, water and carbon dioxide. Sodium bicarbonate is also used in soda acid fire extinguishers where it reacts with sulfuric acid to release carbon dioxide. This carbon dioxide extinguishes the fire. Sodium bicarbonate is useful in the preparation of carbon dioxide gas. When heated strongly, it decomposes to form sodium carbonate, carbon dioxide, and water. Sodium bicarbonate is also used in the manufacture of baking powder. Baking powder is a mixture of sodium bicarbonate and tartaric acid. When baking powder is heated, sodium bicarbonate decomposes to produce carbon dioxide, water, and sodium carbonate. This carbon dioxide that is produced causes the cake to rise, making it light and spongy. The tartaric acid present in baking powder neutralizes sodium carbonate and prevents the cake from becoming bitter. We are familiar with bleaching powder, which is generally used as a disinfectant. Let us now learn more about bleaching powder. Bleaching powder. The chemical formula of bleaching powder is CaOCl2. It is a white powder. It is produced by the action of chlorine on dry slaked lime. When bleaching powder reacts with water, it releases chlorine gas. That is the reason why bleaching powder gives a strong odor to water when it is used to disinfect water. When bleaching powder is exposed to air, it combines with carbon dioxide to form calcium carbonate and chlorine gas. This is the reason why bleaching powder is also known as chloride of lime, and the chlorine generated is called as the available chlorine. This chlorine gas released helps in the bleaching action of cotton in the textile industry, wood pulp in paper industry, and in the bleaching of washed clothes in laundries. The quality of bleaching powder is rated as per the amount of chlorine generated. Greater the amount of available chlorine, better is the quality, as more effective will be the bleaching power. Bleaching powder is used in the preparation of various organic solvents like chloroform, which is an anesthetic. Bleaching powder produces nascent oxygen, hence it is used as an oxidizing agent in many chemical reactions. We are familiar with the use of washing soda as a cleansing agent. Let us learn more about washing soda. Sodium carbonate, washing soda. Washing soda is sodium carbonate decahydrate. Its chemical formula is Na2CO3 10H2O. Washing soda is alkaline in nature. If we test a solution of washing soda with blue and red litmus papers, blue litmus paper does not show any change, while red litmus paper turns blue. Washing soda has various applications. It is used in the manufacture of detergent powder, glass, soap, and paper. It is also used in the manufacture of sodium compounds like borax. Water becomes hard due to the presence of chlorides and sulfates of calcium and magnesium. Sodium carbonate is used in the softening of hard water. Crystals of salts. Activity: take a few crystals of copper sulfate in a test tube. Heat it. What do you observe? The blue-colored copper sulfate has turned white. There are droplets of water on the inner sides of the test tube. These water droplets are called water of crystallization. Some compounds like copper sulfate have a fixed number of water molecules in their crystals. When such compounds are heated or exposed to air, they lose these water molecules and turn into a substance called as anhydrous substance. Copper sulfate loses water to form anhydrous copper sulfate. What will happen if you add water to anhydrous copper sulfate? The blue color of copper sulfate reappears. Copper sulfate crystals contain 5 molecules of water of crystallization. That is why the formula of copper sulfate is represented as CuSO4 5H2O. Such salts containing water of crystallization are called hydrated salts. Washing soda also is a hydrated salt. The 10 molecules of water in washing soda are the water of crystallization. Water of crystallization is a part of the crystal structure of a salt. It is not free water, therefore it does not wet the salt. Thus, salts containing water of crystallization appear to be perfectly dry. It gives the crystals of the salt their shape and in some cases imparts them the color. Every hydrated salt has a fixed number of molecules of water of crystallization in its one formula unit. Some other examples of compounds with water of crystallization are gypsum CaSO4 2H2O and plaster of Paris 2CaSO4 H2O. Plaster of Paris. Plaster of Paris is calcium sulfate hemihydrate. Its formula is CaSO4 half H2O. The formula CaSO4 half H2O actually means that 2 molecules of calcium sulfate share 1 molecule of water, so the effective water of crystallization for 1 calcium sulfate unit comes to half molecule of water. Plaster of Paris can also be written as 2CaSO4 H2O. It is a white powder. It has a very remarkable property of setting into a hard mass on wetting with water. Plaster of Paris is used in making toys and decorative materials. It was first made by heating gypsum, which was mainly found in Paris. Therefore, it is named as plaster of Paris. Gypsum is calcium sulfate dihydrate. It contains 2 molecules of water of crystallization. On heating gypsum to a temperature of 100 degrees Celsius, gypsum loses 3/4 of its water of crystallization and forms plaster of Paris. If gypsum is heated above 100 degrees Celsius, gypsum loses all its water molecules and forms anhydrous calcium sulfate called dead burnt plaster. This dead burnt plaster does not set like plaster of Paris on adding water.